Hi, today I wanted to speak to you about the SST Sensing's optical oxygen sensor, which we call LuminOx, as an example here. We developed this sensor a few years ago because we believed there was a demand in the market for a non-depleting and ROS-compliant sensor. So the competition here is typically galvanic and electrochemical sensors, some of which contain harmful substances such as lead. They're still allowed to be sold despite not being ROS-compliant. But that can't last forever because we can't continue to make sensors with lead in them. The other problem is that these sensors deplete over time, so they simply wear out a bit like a battery. One of the other issues is that the more oxygen they see, the faster they wear out. So their lifetime's not really well known. When you unpack one or when you buy one, you don't really know how long it's going to last because you don't know necessarily what environment it's going to be in terms of the amount of oxygen. So we developed the LuminOx oxygen sensor, and it's based on optical fluorescence quenching. So inside here we've got a blue LED which emits pulses of high energy blue light. That blue light hits a fluorescent material which fluoresces and gives off an orange light. Now the amount of light that it produces then decays over time, and it decays over a short time of the order of a few microseconds. And in the presence of high oxygen concentration, then the decay rate is pretty fast, and in the presence of low oxygen concentration, then it's slower. The microcontroller on board measures the time it takes for that waveform to decay, compensates for temperature, and then provides an oxygen value based on that. We calibrate every single sensor in the factory here at SST. So the sensor, unlike electrochemical sensors and galvanics, which typically have 3 pins and take no power, this sensor does need power. It needs a 5-volt supply on these 2 pins, and then these 2 pins here are the comms pins. So rather than producing an analog output, which needs to be signal conditioned, amplified, temperature compensated, this sensor has got a fully compensated, fully calibrated output, and we communicate the oxygen value via these 2 pins. Now we chose to make it an RS-232 TTL level compatible interface because it's a very simple way to connect to a microcontroller just through the micro's UART. So 5 volt goes to these 2 pins, 3.3 volt nominally TTL signal straight into your microcontroller. That's 5 volt tolerant, but most microcontrollers are 3.3 volts. So unlike other sensors of a similar style and size, you don't need any external circuitry, just your microcontroller, and every product's got a microcontroller these days, so really you've eliminated the cost of additional circuitry. I've got an example one here connected up, and we've just simply connected it to a USB interface, a USB to RS-232 interface, and I'm recording my screen so you'll be able to see that in a window when you watch this video. I'm just going to apply power to it, so I'm just going to apply the 3.3 volt signal to it, or the 5 volt signal rather. You can see it starting to produce oxygen values. So it's saying 20.67, which is pretty good. It's typically 20.7% oxygen in most normal indoor environments, not 20.95. 20.95, or the 21% that most people think of oxygen being the oxygen content in air, that's based on the air being dry. Of course there's some humidity, so that oxygen value gets diluted a bit. So 20.7 is pretty typical. We're measuring 20.6 something. You see on the screen that we've got over here, we've got the oxygen pressure in millibar. So it's saying up here, it's saying 208.4 millibar. The temperature inside the sensor is 25 Celsius. The barometric pressure, because there's a pressure sensor inside here, is 1009 millibar. And we use that pressure value and the oxygen pressure value to calculate the oxygen concentration. Here we're saying it's 20.62. This one, you can see the bottom go down a bit, probably because I'm breathing a bit of CO2 onto it. I'll put lots more CO2 into it now. So you can see the oxygen's dropped now to below 19.5%. It's going to keep on going. Then it's going to start rising up again now that fresh air is drifting back into the sensor. The gas gets in through this porous PTFE hydrophobic membrane, which keeps stuff out of the sensor, particularly moisture and dust. So that has a relatively slow response time because of that. And because I was just breathing gently, if you were to direct a gas on there at higher flow rate, then the response time would be faster. That's the standard sensor. I'll just let that carry on running. We've got some other sensors here. So when we launch the product, we launch with this product, which is the standard one. So the gas can enter here through the front face, but it can also actually get in through the gap between the case and the cover, because that's not a gas-tight seal. That's fine for many applications where you just want to measure the oxygen concentration just in the environment around the sensor. We've also released this one, which we call the -S version. It has a -X suffix, and it's fully sealed at the back with epoxy. That means the only way gas can get in is through the filter at the front. That means you could use it in an application where it was sealed here. You have the gas of interest on this side, and you could have some other gas like fresh air, for example, outside the sensing area. If you used the original sensor for that, then you would end up with a mixture of the two gases inside, and you'd get an incorrect reading. You wouldn't be measuring what you wanted to be measuring. And finally, we've recently launched this version, the -F version, F for flow-through. It's got an inlet port and outlet port. It's also sealed at the back, and it's designed to go into instruments and so on, where you might have an inlet port, an outlet port, and you'd have a pump pumping the gas through. Something to be aware of is that there's no filtration in this one, so it's up to you to make sure that the gas is clean and dry before it goes in here. You get a significantly faster response time with this because you're flowing gas right into the sensor and across the sensing membrane rather than letting it diffuse through the PTFE filter. A number of our customers have connected these to things like Arduinos, and that works very well. Obviously, if you're making your own electronic circuit, then it's much easier just to go straight into your microcontroller. And finally, we offer this board called the LuminOx EVB for LuminOx Evaluation Board. The idea here is that we've got a board where it's really for customers who don't want to write their own software, and they don't want to produce their own PCB to start with. You stick this sensor on the board, you give it a 5-volt supply, and it gives you 3 outputs. It gives you an industrial 232 output, so you can talk directly to a PLC, say, that's got an RS-232 interface, or any kind of industrial RS-232 interface, rather than the TTL one that I'm demonstrating on the laptop. It's also got an RS-485 industrial interface, and finally it's got an analog output. It's a very simple 0 to 5 volt signal representing 0 to 25% oxygen, so a very quick way just to get to test the sensor and make sure that it does what you wanted it to do. But customers typically will design their own circuitry because, as I said, all it needs is 2 pins, the 2 UART pins in a micro, so it really couldn't be simpler. So that's all I've got to say about the LuminOx sensor. If you have any questions, then please send them to technical@sstsensing.com, and you can buy these sensors direct from us or from a number of our distributors. Thank you.